Hi friends, today let us discuss about cryptographic hash functions. Let us first try to understand what do you mean by hash function. Hash function is just a function which accepts variable length block of data m as input and output fixed size value h, which is a function on m. So this is called a hash function. The hash values are evenly distributed and random. You cannot compare that with the input message because they are random in nature. Also, hash functions are used to check the data integrity of the message sent from sender to receiver. We will try to compare whether the data received is same as it is sent. In general, the hash function takes arbitrary length input message m and produces fixed length output h. But input will be padded to fixed length, for example 1024 bits, and this padding includes the length of the message and remaining will be padded with zeros. As I said already, hash function, the objective is the data integrity. Now let us discuss about applications of cryptographic hash functions, where cryptographic hash functions means they are hash functions used for security applications in communication. And in this part of the lecture we have taken two examples or two applications, namely data authentication or message authentication and the digital signature. Let us discuss message authentication here now. In message authentication, hash function is used to verify the data integrity, and when a hash function is used to provide message authentication, the hash function value is referred to as message digest. Of course, message authentication assures that the data received are exactly as it is sent. Let us assume a message has to be sent from sender to receiver using hash function now. It works like this. A sender takes message m using a function h. He generates a hash value which is appended with the message for the transmission. Now message appended with the hash value will be transmitted to the receiver like this. Now at the receiver side, the receiver take the message and again the receiver generate a hash value of it, and it compares with the hash value which is generated by the sender like this. If the hash value sent by the sender and the hash value generated by the receiver are same, then it ensures the message is authenticated, means the received message is same as it is sent. Now let us assume that there is a hacker in between sender and the receiver like this, and this information sent by sender will be hacked by the hacker like this. The hacker takes the message which is appended by hash value h. What he does is, the hacker takes only the message out of the message appended with the hash value. He takes only the message and he want to change it or he want to corrupt it. He will change the message to message dash or message cap. The new message will be used to generate a new hash value using the hash function h, and the hash value generated here will be different from this hash value, and the hash value generated by this h will be appended to the message, and this message appended with the new hash value will be transmitted to the receiver. Now you just see here, message is also changed and corresponding hash value is computed by the hacker, and now this message is transmitted to the receiver. At the receiver receives the message appended with the hash value. He take only the message to compute the hash value again, and this computed hash value and the received hash value will be compared. Of course here the received hash value and the computed hash value will be same. It means the receiver thinks that the message is exactly same as it is sent by the sender, but here the message is transmitted and it is hacked by the hacker, where it is morphed or changed by the hacker, and that is sent to the receiver, and receivers think that this is a message which is sent by the sender. So this is called man in middle attack when we are using a hash function. Now the challenge is, the hash value generated by the sender must be protected, because in the previous case what has happened, the hash value generated by the sender has been changed to a hash dash. if we are able to protect the hash value generated by the sender, it will not be changed by the hacker, and same H will be sent to the receiver, where he will compare the value of the hash value received and the hash value generated, and of course it will not be same. Then receiver will easily understand that there is something has done in between. Hence there is a need for protection of hash value generated by the sender. We have 4 techniques here. Let us discuss one by one. This is a type 1 technique where we have a source here and we have a destination here. Here the message will be appended with the hash value generated using the message. Just see here, this is a message and this is a hash function where the input will be the message and the output will be hash value, and this hash value will be appended with the message, and that is given for the encryption. And here we are using symmetric key encryption with the key K, and ultimately what we are doing here, we are generating a hash function which is appended with the message, and that is encoded with the key value K, and that is transmitted. At the receiver side, first receiver decrypt the message whatever he has received with the same key K, and then he will get message which is appended with the hash value. And then what we do is freshly he computes the hash value of M and he compares with this hash value. If the hash values are same, then it means that the data is protected or there is a data integrity. Otherwise the data what he receives here is not same as this. So this architecture or this protocol ensures that the hash value and the message both are protected, because here the message and the hash value are given for encryption. Hence message as well as hash functions are secured, means there is a assurance for data integrity, and also there is a something called data confidentiality, because message is also encrypted, hence you can assure data confidentiality. And the second method to protect the hash value is like this. Here what we do is, instead of encrypting both message and also hash value, we encrypt only hash value here. We take a message M and we generate a hash value, and the hash value will be encrypted using the symmetric cipher model using the key K, and that output of that encryption will be appended to the message, and that is transmitted. And at the receiver side, he splits message as well as hash value which is encrypted, and he compute fresh hash value for this message, and this hash value which is encrypted will be decrypted using same symmetric cipher model with the same key K, and these two values will be compared, the hash values. If these two values are same, it ensures you data integrity. Otherwise we can assume that data sent by the sender is not same as the data received by the receiver. In the third method, what we do is we try to add more security to the previously discussed architecture. Here the message is given to the hash function. Before to that, we use a secret key which is appended with the message, then we will give it to hash function. And this hash function generates hash value that will be appended to the message and it will be transmitted. And at the receiver side, we split message as well as hash values, and we use message to generate hash value. Of course, before hash value generation, same secret key will be appended to the message, then hash value is generated. And of course that hash value will be compared to the received hash value. If these two hash values are same, then it ensures data integrity. Otherwise you can easily assume that there is a problem with the communication or the message is hacked. Let us see the last type of hash value protection. Here what we do is, we combine the previously discussed two protocols where message appended by a secret key will be given to hash function, and output of hash function will be hash value, and that will be appended to the message. And message and this hash value are given to encryption or ciphering with the private key encryption where key is K, and that is given for transmission. And after transmission, receiver receives that and it decrypts, because it is encrypted, and the receiver decrypts it with the same key. And after that, it splits message block and hash block. And we know that message block should be appended with the secret key S, because in the transmitter side we have used the secret key S, which is appended to the message. Here again we append the secret key S to the message, and that is used to generate a hash value. If the hash value generated here is same as the hash value received, then it ensures data integrity. Otherwise you can easily assume that the data is hacked. The another application of hash function is digital signature. We all know what do you mean by digital signature. In previous classes and all we have discussed this. However, we will try to understand some protocol related to digital signature. What do you mean by digital signature? Digital signature ensures you the identity of the sender. Here we use message M to generate a hash value using hash function H, and that is given to a public key crypto system where the key is private key of a sender. We know how a public key crypto system works. We use a private key of transmitter or a sender for the encryption, and the output of that will be appended with the message, and that is transmitted. And at the receiver side we split the block of message as well as the encrypted version of the hash function, and we use message to generate the hash function. And since this hash function is encrypted, we have to decrypt it. Let us decrypt using public key of the receiver. PU means public key of the receiver. So this means transmitted using or encrypted using private key of A, decrypted using public key of B. So this is the concept of public key crypto system. And after decryption, if the hash value generated and the hash value decrypted here are same, it ensures digital signature. Means it assures you that it is sent from the sender A only, because it is encoded using a private key of A, which is not known to anybody. And in second type of digital signature protocol, what we do is, of course we do the same thing here. We use a message to generate a hash value using hash function H, and that is given to encryption, where we use a public key encryption technique with the key which is with the private key of the sender, and that is appended with the message, and this part is same as the previous protocol. And after this we use private key encryption with the secret key K, and we transmit that. And at the receiver side, the receiver decrypts whatever the data received with the same key K using private key encryption technique. Then after that, message block and the encrypted version of the hash blocks are separated, and the message is used to generate a hash value as we done here. And the encrypted version of the hash is decrypted using public key cryptography or public key crypto system. Like here we have encrypted using private key of A, so we have to decrypt here using public key of B, and that should be compared with the generated hash value. If they are same, it ensures digital signature. If the decrypted hash value is same as the hash value generated here, then we can easily think that it is digitally signatured, or the message M is transmitted by the sender A only. The difference between the first type and second type is very simple. Here we use only hash value for the encryption, and message is not encrypted here, whereas in this case message as well as the hash value are encrypted. Hence this assures you digital signature, and this assures you digital signature as well as message confidentiality.